Today we are learning about 2.7, parent functions and transformations. Families of graphs is a group of graphs that display one or more similar characteristics. Parent graph, also stated as the parent function, is the simplest of the graphs in the family. Constant function general equation, is f of x, or function of x, equals a, where a is any number, like y equals 2. Domain is all real numbers, and range of a. Identity function, it says identify, is f of x equals x, a line passing through all the points of AA, meaning whenever value you plug in, you will get the exact same value when you plug it out. The domain and range is all real numbers. Absolute value function, the domain is all real numbers, and the range is y is greater than or equal to 0 for the parent function. Quadratic function, all real numbers, and the range is y is greater than or equal to 0. Translations is a type of transformation where we slide a figure up, down, left, or right. When the constant k is added or subtracted from the parent function, the result is plus or minus k. It is the translation of the graph vertically, so we move the graph up or down. When the constant x is added or subtracted from, this should be h, is added or subtracted from x before evaluating the function, the result is f of x plus h, or minus h is the translation horizontally. This should be the opposite of what you see. Reflection. It flips a figure over a line called a line of reflection. We learned about this in geometry. When a parent function is multiplied by -1, the result is negative f of x, and its reflection across the x-axis, which is the y equals 0 line. Only when a variable is multiplied by -1, the result is f of negative x, which is reflected across when the y-axis. Dilation shrinks or enlarges a figure proportionally, stretch or compress vertically. So what we're going to do is we're just going to name some functions. This is the identity function. This is an absolute. And this is a quadratic. Identity is a linear function. Absolute is a v function. Quadratic is a smiley face, frowny face, valley, hill. It has a curve, and you have one low point or one high point. The next what we're going to do is we're going to do translations, and then we're going to graph the functions. What I'm actually going to do is I'm going to graph the parent function first, and then I'm going to talk about the translations. Parent function I'm going to do in light blue color. For a quadratic equation, the parent function of y equals x squared has the starting point of 0, 0. And the rule is if you go right 1, you go up 1. If you go right 2, you will go up 4 because you're going to square what your movement is. So if you go right 2, you're picking a point to the right 2. And when you plug in the equation, you would square it and go up 4. Same thing if you go 1. 1 squared is 1. So parent function, 0, 0, right 1, up 1, right 2, up 4. It is mirror crossed, or I go left 1, up 1, left 2, up 4. This is the parent function, which works as this, or looks as this. The transformation or translation, this is a k value of -4, so my points are all going to shift down 4. So I'm going to take every single point and move it down 4. So 1, 2, 3, 4 moves my starting of hk from 0 to -4. And using the rule, I can just go right 1, up 1, right 2, up 4 from here. Or from my parent function, I can count my points down, each one 4 points. So the dark blue function is the parent function after the translation. Alright, absolute value. Parent function is y equals the absolute value of x, and I start at 0, 0. So starting here. And then my slopes are of 1. Now, with the plus 1 being on the inside, with the x, that's my h, so my h is actually minus 1, 0. So all my points are actually going to shift to the left. So I'm going to go to the left, 1. So each point is going to shift to the left 1. And there you go. So light blue, parent function, dark blue, the shifting after I move left 1. Reflections, if it is outside the function, it is reflected across the y-axis, so absolute value, parent function. Looks like this. Reflection, this is a reflection across the x-axis. So everything's going to flip down. So when I got my answer, so when I plug in 1 to the equation, if I plug in 1, I get the answer of 1, but then I'm going to take the opposite of it, so it's going to shoot it down to the other side. This is how absolute values become negative, because you're taking the opposite of the answer that you got from when you plugged in a point or evaluated a point value in. So light blue, parent function, dark blue, reflection across the x-axis. So parent function on the inside, quadratic, right 1 up 1, right 2 up 4, right 1 left 1, or left 1 up 1, left 2 up 4. So what happens here? So on the parent function, I have a 1, and I plugged it in, I got a 1. But when I plug in the 1, it actually jumps me over here to negative 1, and then I get this answer. So this point actually reflects over to here, and then I get the value answer. So when I reflect across the y-axis with the inside points changing, the reflection doesn't really do anything to a quadratic or an absolute value, but linear it would switch your points. So it changes the signs of your x's, but your y's will stay the same answer. So that keeps me the same thing, but this is a reflection across the y-axis. Just remember the difference between the two. If it is inside with the x, it's across the y-axis. If it's outside of the function, it's across the x-axis. Alright, dilation of the function. If it is a dilation here, this is a vertical stretch or compression. You can just say vertical stretch of 3/5. So this has a vertical stretch of 3/5. So what does that mean to our parent function? So parent function is the identity function, which is the slope of 1. So what happens is my HK is still at 0, 0, but instead of going up 1 to the right 1, I'm going to actually go up 3 and to the right 5. So I'm going to circle out my points here, and another color after I connect these. And these points here are actually a huge change. So my first point here and here actually stretched out this far, or you can think about it as I moved out 3 and up a fifth. So 3/5 of the way, instead of moving 1, I actually shrunk down here, and it could be these points here as well. I like to think of it as we are moving the first point out that far. Okay, with the quadratic, it makes it a little bit easier. So the scale is 1, so with the parent function, right 1, up 1, right 2, up 4, always back from the previous first point that you start with. I'm going to graph those out, and then instead of going right 1, up 1, what happens, you're going to go up 1 times 3, because we are stretching the vertical stretch. Going right 2, up 4, we're actually going to take this times 3. So this first point here gets stretched even more. So this has a vertical stretch of 3. So instead of moving right 1, up 1, I'm going to move right 1, up 3. So it moves the point right 1, up 3 to here, and I get a long skinny graph. So the pink points are actually now these points. Okay, so this graph here is we have a shift in movement to the right 12, and then we have a vertical stretch. And so with this one, all I care about here is really saying that you go right 12, and then you have a vertical stretch of 1/2. So if I'm going to go right 12, my graph is going to go from original function of a v, okay, and then I'm actually going to move it over 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I don't have enough spots. So what I'm actually going to do is I'm going to go by 2. So 0, 2, 4, 6, 8, 10, 12. So I move to the right 12, and then instead of going up 1 over 1, I'm actually going to go right 1 up 1/2. So I move half the distance. So I'm going to go right 1 up 1/2. So if I'm doing that by a scale of 1 here, so my x's are by 2s, and my y's are going to be by 1, so you know my scale. If I go over 2, I'm going to go up a full 1 value. So keep going up 1/2 instead. So if I go right 2, it'd be up 1. Right 1 would be up 1/2, so these would be my halves. So this is my new absolute value. Now it kind of looks the same because I changed my scale, but otherwise it'd be really, really wide. So there you go. That's your lesson.